Principle of the increase of entropy. The principle of the increase of entropy for a control mass analysis was discussed in the Chapter 8. The same general conclusion is reached for a control volume analysis also. This is demonstrated by the split of the whole world into control volume A and its surroundings, control volume B, as shown in this picture. Assume a process takes place in control volume in this picture, and exchanging mass flow, energy, and entropy transfer with the surrounding. Mass flow, energy, and entropy. Transfers with a surrounding. Precisely where the heat transfer enters control volume A, we have a temperature TA for control volume A. We have TA, and for control volume which is not necessary to the equals to the ambient temperature far away from the control volume. First, let us write the entropy balance equation for two control volume as this relation. M dot I S I M dot E S E plus Q dot on T A S generation A. And D is control volume B on dt start generation B. Which is not necessary. First, let us write the entropy balance as these two relations for control volume A, which is shown in this picture, and control volume B, which is also shown in this picture, which is between the control A and control volume, the ambient. And notice that the transfer terms are all evaluated right at the control volume surface. Now we will add the two entropy balance equations to find net rate of change of S for the total work. The total ds control volume A on dt plus ds control volume E on dt. M dot I SI minus M dot ESE plus S dot generation and A minus M dot I SI plus M dot ESE minus Q dot on TA plus S dot generation P. As the result, we have ds net on dt S dot generation S dot generation B is greater than 0. Here we notice that all the transfer terms cancel out in this relation. ds net on dt S dot generation A plus S dot generation B all the transfer terms cancel out. Leaving only the positive generation term for each of the words. The positive generation terms. The positive generation terms for each part of board. If no process takes place in the ambient, that generation tends is zero. However, we also notice that for the heat transfer to move in the identical direction, we must have T be greater than Ta. That is, the heat transfer takes place over a final temperature difference. So an irreversible process occurs in the surrounding. Such a case is called the external irreversible process. This distinguishes it from any generation of S inside the control volume A, then called an internal irreversible process. It from any generation of S inside the control volume A inside the control volume. This equals the integration of the A and then called internal irreversible process. For this general control volume analysis, we arrive at the same conclusions as the control mass situation. The entropy for the ideal world must increase or stay constant. The entropy of the total world must increase or stay constant. In this case, we have ds only those processes that satisfy this equation can possibly take place. Any processes that would reduce the total entropy is impossible and will not occur. Some other comments about the principle of the increase of entropy are in order. If we look at the evaluate change in the state for various parts of the world, we can find the net rate by the left hand side of the equations of and thus verify that is positive for process we consider. Start generation greater than 0. Notice that the left hand side sums the storage, but it is not explained where the entropy is big. If we print want to detailed information about where the entropy is made, we must make a number of control volume analyses and evaluate the storage and transfer time for each control volume. Then the rate of generation is found from the balance, that is from a summation of various generation form, and that must be positive or at the least zero. So not only must the total entropy increase by the sum of generation terms, but we also must have a positive or at least zero entropy generation in every considerable process that locally generated entropy will happen, and any process that locally would destroy entropy cannot take place. Remember, these not preclude that entropy for some mass decrease as long as that is caused by a heat transfer out of the mass. That is, the negative storage is explained by a negative transfer term. When use this equation is the generation greater or equals to 0 to check any particular process for a possible violation of the second law. There are situations in which we can calculate the entropy generation directly. However, in many cases it is necessary to calculate the entropy change of the control volume and surroundings separately and then add them together to see if these equations satisfy. In these cases, it is preferable to rewrite the equation for surrounding B to account for the fact that the heat transfer originates at temperature Tb. This means that the entropy generation B is given as this relation control value on dT for example m dot for a control value B is on m dot B is E Q dot on TB. For the steady state process, we realize that the first expression is equals to 0, so that all the entropy increase is observed in surrounding B. Let me write the relation again. T is control value B on dt for a steady state. We realize that so that all of the entropy increase is observed in surrounding B, and this can be calculated from this relation, where for a transient process there are both control value A and surrounding B terms to evaluate. Each term is integrated over the time t of the process, as was done in the previous section. The integration was delta S net and delta S control volume A, control volume A. The term for sounding is after applying to the sounding and interacting delta S MESE The last section is engineering application and efficiencies.